Are you ready to explore nothing less than the entire universe?
3, 2, 1.
Welcome to Nova Now Universe Revealed, a 5-part companion podcast series to the Nova miniseries on PBS. Humanity's view of the vast cosmos is part of our global heritage, and you can check it out anywhere on Earth. Take stars. We typically think of them as part of the night sky, but it's a star that dominates our days. The sun, our primary provider of light and heat. Look around outside. Plants, from the tallest trees to the shortest sprouts, stretch out reaching towards the light. And these plants convert our star's energy into fuel that we can consume to power ourselves. But have you ever looked up and wondered, what exactly is a star, and why is it shining? Well, Timon and Pumbaa have from The Lion King.
Timon,
Yeah?
ever wonder what those sparkly dots are up there?
They're fireflies. Fireflies that got stuck up in that big bluish black thing.
Oh, gee. I always thought they were balls of gas burning billions of miles away.
Sorry, Timon. Pumbaa got this one right. But, plot twist, fusion scientists today are trying to capture the power of the stars in a magnetic bottle. Feeling starry-eyed yet? Today on Nova Now Universe Revealed, stars, what makes them shine, how we're trying to recreate that energy source here on Earth, and how you and I are composed of stardust. I'm Alok Patel.
Solar energy is indirectly responsible for damn near every process on Earth, right? When you eat, that's the sun.
This is Hakeem Oluseyi. He's an astrophysicist and cosmologist. And as he puts it,
I am a science mercenary.
I called on Hakeem to help me understand those twinkling lights in the sky and how they shine.
So, a star is a self-sustained nuclear fusion reaction in a center of a giant ball of gas and plasma. So it's the fusion reaction that's the key thing.
For those of us who aren't nuclear physicists, can I get a show of hands, people? Let's do a quick refresher on atoms. They're the basic units of matter, made up of 3 types of particles: protons, electrons, and neutrons. Protons have a positive charge, and the number of them in an atom's nucleus determines which element it is. You might remember the periodic table of elements from science class. 1 proton means you have hydrogen, 2 protons, helium, 3, lithium, and down the line. The second kind of particle, electrons, have a negative charge, whereas neutrons, the 3rd type of particle, have no charge. So when it comes to fusion, a fusion reaction is nothing more than 2 lighter atoms merging to form a heavier atom, an entirely new element. It's the nuclei of the atoms that fuse together. And this process releases energy because the total mass of the resulting element is slightly less than the sum of the 2 originals. That leftover mass is released as energy. But nuclei don't just fuse together on their own. In fact, their protons naturally repel each other due to their positive electric charge. So to get fusion to happen, you have to meet certain conditions.
And the primary conditions, there are 2 of them. Like with many things that occur that involve matter, the 2 things that are almost always the most important are the temperature and the density, how much stuff is packed together.
And the temperatures and densities required for fusion are found inside the cores of stars.
When you think about a star really has 2 major parts. It has a core where the fusion reaction is going to occur. And then between the core and the surface, that region of the star, we call that the envelope.
It's the gravity of the star that keeps its core hot and dense.
As you pour more and more matter onto that envelope, it's compressing that core more and more, making it hotter and hotter and hotter. Imagine 2 protons that are in that core, and they're flying around and they're coming towards each other. what's going to happen is they're going to veer away from each other. Now, as the temperature gets hotter and hotter, that means the particles are moving faster and faster. This means that when those two protons are encountering each other, they get closer at a higher speed than they would get at a lower speed. And the key thing for them is to get within a certain distance of each other. Then there is a strong attractive force that kicks in that we call the strong force. That's 137 times more powerful than the electrostatic repulsive force. So instead of veering away, they'll be pulled together. These two protons now in this core getting crushed by this envelope scream towards each other. The temperature is 10 million degrees Kelvin. And so now, boom.
Boom, meaning once atoms start fusing together, you've got yourself a star.
That's the first step of what we call the PP chain. P, the letter P for Papa, stands for proton-proton chain, right? And so we typically say hydrogen combines to form helium, but it's a series of steps where ultimately you end up with two protons and two neutrons bound together in what we call a helium-4 nucleus.
In other words, two 1-proton hydrogen atoms have fused into one 2-proton helium atom.
And in that process, you kick out light in the form of gamma rays and neutrinos.
Fuse enough hydrogen into helium, and you get a star that shines. Stellar fusion's also responsible for fusing nuclei into not just helium, but even heavier elements like oxygen, carbon, nitrogen.
If you look at the order in which stars build atoms in their cores, and you look at the abundance of the elements in the universe, you'll see directly that stars built the stuff. You know, what boggles my mind is every time you take a breath, you're inhaling the cores of long dead stars. That's where these atoms came from.
So it's fair to say like stars play an important part in terms of the formation of elements in our universe?
Oh, they play the primary part. So basically, there are several processes by which elements are created. And the creation of the elements we call nucleosynthesis. So there are processes that occur in the cores of stars. Now, there's another way that's more sneaky. And that's when neutrons sneak into a nucleus. Neutrons do not have an electromagnetic repulsion, right? So they can, I'm flying out of the core and I'm flying around the envelope. Boom, I hit a nucleus. I am now part of that nucleus.
And sometimes that neutron converts into a proton, which transforms the atom into a different element.
And that way you build up heavier elements, right? Then there is the process of a supernova explosion.
A supernova, the end times for giant stars. When a massive star much larger than our sun runs out of nuclear fuel, the energy from the fusion no longer balances the force of gravity, and some of its mass from the envelope falls into its core. Eventually, the core gets so heavy that it can't withstand its own gravitational force. The core collapses in on itself, and the massive star explodes in a giant supernova.
The inner core goes out, so the outer layers just fall in at, some fraction of the speed of light. And so now you can really, once again, sneak protons into nuclei,
which generates heavier elements.
Another thing is when neutron stars collide.
After a massive star goes supernova, its core can become a tiny and incredibly dense object. Just 1 teaspoon of that material weighs 4 billion tons. These super dense cores of exploded stars are called neutron stars.
So if you have neutron stars, that's a lot of neutrons to be packing, boom, right? You can make some really big nuclei. And that's when, our first time we observed 2 neutron stars collide, more than an Earth's mass of gold was produced in the collision.
Wow.
Yeah.
It's hard to even fathom.
Exactly, right? It's crazy.
Thankfully, our sun doesn't have enough mass to go supernova. But there's still the question of what's going to happen when it runs out of hydrogen fuel to fuse.
It's more than a factor of it running out of its gas because there's other dynamics that are occurring. So when a star is burning hydrogen, like the sun is doing right now, they're really stable and well-behaved. Before they start burning hydrogen, they can be crazy. And when they go from burning hydrogen to burning other things like helium, carbon, oxygen, they can behave crazy then, right? But one of the things they will do is they'll swell up. And many of them will pulsate. And some of them will have periodic pulses that originate in the core and throw off the outer layers. The envelope just starts going wacky. You know what I mean? After the star gets a bit old.
And how far away is this reality from our sun?
Our sun is at the halfway point. So we got about another 4.5 billion years. But, we are not going to be there. Earth is going to be uninhabitable in another billion years because as you burn hydrogen to make helium, remember, the core of the sun is not hot enough to burn helium. So that helium that is sitting in the core of the sun right now, it's just sitting there in the core and it's not burning. As the core gets crushed down smaller and smaller, that means that the outer layers, the envelope, is responding to what the core is doing, right? So if the core is hotter and putting out more energy and more heat, the envelope expands. So in a billion years, the Earth is going to be uninhabitable because the sun will have swollen to such a size that the amount of radiation reaching Earth will have, boiled off the oceans. And, once you do that, it's bad.
Life is short. That's even more reason people have to party. You only have 1 billion years left here. And when we return, I'll give you a different reason to party. How scientists are creating a star in a bottle using fusion inside a lab. In the past 100 years, our understanding of nuclear fusion, the process we've been discussing that powers our sun and sustains life on Earth, has exploded. Given that it generates immense power and is responsible for the creation of elements across the universe, fusion's gotten some people wondering if maybe we can harness that power right here on Earth as a new source of clean energy. Here's Maria Zuber, Vice President for Research at MIT.
Well, there's a big push right now in decarbonizing the grid with renewables, solar, wind. But at some point, probably around 2040, we're going to max out with renewables and we won't be able to decarbonize further. We're going to need another zero carbon option.
This is a video from MIT. Its Plasma Science and Fusion Center has partnered with the Commonwealth Fusion Systems startup company to develop commercial fusion as a clean energy source. Dennis White directs the Plasma Science and Fusion Center.
It's like the Prometheus myth. We're going to bring the fire of the gods down here to Earth, although we don't want to end up like Prometheus.
That is, with an eagle eating our livers for eternity. That doesn't sound great. But fusion energy isn't as zany as it sounds.
Almost every energy source that we actually have on Earth actually originates with fusion because wind comes from heating the atmosphere, solar, very evident, which is the radiant energy which comes from the sun. But even fossil fuels are actually fusion energy because they were from plants accumulating stored energy from sunlight coming down to the Earth.
But recreating actual nuclear fusion as a sustainable energy source would be groundbreaking.
The main goal is to bring that fundamental energy source that powers stars to Earth for use by mankind to provide an inexhaustible supply of energy.
I have 1,000 questions.
I mean, sometimes it's a simple answer, and yet it's so, that's kind of ambitious.
First, we need to differentiate fusion from fission, which is a process traditionally associated with the term nuclear energy.
They're literally the opposite of each other. So fusion, as I described, combines or fuses the lightest elements.
Like hydrogen into helium.
Fission actually breaks apart the largest, most unstable elements, mostly uranium. So the thing that they share in common is that because they're making new kinds of atoms, it releases very large amounts of energy per unit mass. And that's almost like where the similarity ends. So in fusion, it's inherently safe because you cannot get a runaway process. The process itself does not produce nuclear waste. Fission has to, by the rules of physics. I would point out the universe already voted. The universe runs on fusion.
Quick rewind to Hakeem on nuclear fusion in stars.
These two protons now in this core getting crushed by this envelope, scream towards each other. The temperature is 10 million degrees Kelvin. And so now, boom.
And get this. This is exactly what scientists like Dennis White are trying to do in the lab. So to get that fusion to happen, the first order of business is to recreate the conditions of a star. That's all. That's easy enough, right? First, let's talk about gravity. To force nuclei to fuse together, you need your lab to be the size of a star because you need that much mass to create a sufficient gravity force.
So that can't be directly translated, obviously, onto Earth. So we have to replace the gravitational force with another kind of force. And our main line of doing this is replacing it with the magnetic force or the electromagnetic force.
Next, consider the temperature.
The fusion reaction needs high temperatures to occur. And the way that this works is what provides the high temperature must be, in the end, the fusion reactions themselves.
In stars, the temperature remains high due to both the pressure from gravity and the energy released by fusion reactions in the core. In other words, fusion powers more fusion, allowing stars to be self-sustaining, at least for a time.
It's like a fire. You need more than just a match. You need more than something that's just hot temporarily. You need the wood to actually burn the other parts of the wood as well, too, by keeping them hot, sufficiently hot. So it's the same thing in fusion. Actually, it works on the same physical principle. You're just trying to keep it hot enough that the fusion, in fact, will occur.
In stars, the temperature has to be at least 10 million degrees Kelvin for fusion to occur. Our sun's core is around 15 million degrees Celsius. But when Dennis says hot, he means even hotter, roughly 100 million degrees Celsius.
In fact, the temperature of 100 million degrees was achieved many decades ago. So the natural question is, well, what kind of container can hold something on Earth that is at 100 million degrees? The answer is nothing.
For comparison, imagine an oven.
So you turn on the element in there, there's heat being released in it, so you put some insulation around on the oven, kind of put some energy into it, don't let it escape out into the kitchen, and it's going to get hot.
But no oven, no matter what the infomercial says, could contain 100 million degrees Celsius.
So what we have to do is actually isolate the fuel from anything that has to do with it being on Earth in a terrestrial environment. And so what does that entail? So first of all, we get rid of all the air. It's gone. So this is why I said it's not like a container than we think of like of a bottle or an oven. We build a different kind of container. And the container is the magnetic field. The magnetic field, because it exerts an action at a distance, allows you to exert a force on those hot particles without physically touching it.
What could possibly survive at such scorching temperatures?
We call it a plasma.
Remember, matter exists naturally in 4 states: liquid, solid, gas, and plasma. Think of plasma as superheated matter. Since the fuel Dennis and his team are using has to be heated in the lab to around 100 million degrees Celsius, it exists as plasma. And just because I'm thinking through doomsday lab scenarios, what would happen if the magnetic field were to, I don't know if it actually would break, but if it lost its integrity and the plasma escaped in your lab?
So it immediately turns back into a room temperature gas because it will touch normal matter and then it cools so rapidly that instantly all fusion reactions stop because it's not hot anymore. And in fact, it gets so cold, it's not even a plasma anymore. It'll just turn back into regular gas. In fact, the challenge about fusion has been to keep it going because it always wants to go back actually to a room temperature gas. We just don't allow it by holding it with that magnetic field. So this is why fusion is inherently safe.
You were talking about the fuel. Now, the fuel in a star is hydrogen in those specific conditions. Is that the same fuel you're using or that nuclear fusion labs are using on Earth?
Yeah, almost that. So what we use is actually a different fusion reaction than occurs in stars. It turns out that the process that occurs in stars is actually too weak and too slow for us to use for a practical power plant, which you would think of as like, wow, isn't the sun making a lot of power? But it's also enormous in terms of its volume. So we actually use a different reaction than what's used in the sun. So we use a heavier form of hydrogen. It's called deuterium. And it's around 1 in every 5,000 hydrogen atoms is a deuterium one. It's just twice as heavy. So it's abundant everywhere that there's water. And we extract that one small percentage of it. And you go, well, that doesn't sound very effective because is it going to use a lot of water? Well, no, because This has to do with the effectiveness of fusion, is that, like as you were picking up your coffee, like the amount of deuterium that is in that cup of coffee is approximately like what's needed to power all of your personal energy needs for a year, is just in that one cup of coffee. And yet you're extracting essentially an infinitesimal amount of water. So this is why we say for that fuel source, it's essentially limitless, because just think of the amount of water that's around everywhere.
The amount of water in my coffee, the deuterium in there was enough to power my apartment for a year. And what's funny is the coffee itself is barely enough to power this podcast host for a couple hours.
Yes.
Scientists have been able to fuse elements in the lab, but one of the challenges they still face is reaching net energy gain, or getting more energy out than they put in. So before fusion becomes the power source feeding the outlets in the walls of our homes, we have to address the question of how to get fusion to power itself, to become self-sustaining, like it is in stars.
We call this the burning plasma, which again goes back to the analogy of a pile of wood sitting in your fireplace is different than when it's burning. So when it's burning, this means that the fusion reactions and the particles which are being released in fusion are themselves then keeping the medium hot so that more fusion reactions can occur. That has not been achieved yet. Then you say, okay, so once you achieve that, are you all the way there? We're not all the way there, because the other part of it is that as a practical energy source, you have to meet obvious things of reliability and particularly economics. So can you build them fast enough? Can you build them cheaply enough that you can actually pay yourself back for the resources that it took to build this object? We honestly don't know the answers to those yet, but we are working very hard at understanding about what is needed to get there.
I was going to ask you, what's taking so long? Why aren't we there yet? What is so hard? And I'm curious to get your blunt answer. And what is the limiting step right now?
It's the perfect question. Why is it taking so long? It's not because we don't understand the science of fusion, in my opinion. What happened was the objects that we had to build, these very special objects of magnets, became so big and complex that it just kind of really stopped, in my opinion, innovation. And it also slowed down the timescale of actually achieving these conditions that were necessary.
But on September 5th, 2021, Dennis and his research team demonstrated a breakthrough in fusion technology.
We have, in fact, achieved 20 Tesla for the first time in a large bore fusion-relevant coil. And what this means is that we're going to change the trajectory of fusion energy, and we hope the world, by supplying clean energy to mankind forever.
That's Dennis speaking at the Commonwealth Fusion Systems demonstration event that was live streamed on September 5th.
Along with our private sector, partner Commonwealth Fusion Systems, we demonstrated a magnet technology that basically put us on a completely different path, the same science path to fusion, but a totally different scale and economic viability path to fusion.
And brace yourself, here was their big breakthrough.
We made a magnetic field that has a unit of around 400,000. So it's 400,000 times the Earth's magnetic field. And why is this important? The simple answer is that of doubling the magnetic field strength increases the amount of fusion power that you get in a fixed volume to the fourth power of that doubling. So that's what we did. We basically doubled the magnetic field compared to the previous technology.
Which means a 16-fold increase in the amount of fusion power. And they did it using high-temperature superconductors, extremely powerful magnets that consume negligible amounts of energy.
Now I can build an object a lot smaller and make the same amount of fusion power, which is good from a speed point of view, but also obviously critical from an economic point of view. It also allows you to get to that special science condition that I talked about that we haven't crossed over the threshold yet of when the plasma starts to heat itself and we get net energy gain. But it actually has a real shot at meeting economic targets for the first time. So we think that this is why it's the game changer, to use an overused word, but it is a game changer.
I mean, I don't think it's overused if the game changer is a limitless source of green energy that could basically power mankind until we cease to exist.
Yes, yes.
I would call that the game changer.
Of course, I worry. What do I worry about? It's easy. We're not going fast enough. It's mostly motivated by climate change and the timelines of climate change.
Scientists at MIT have estimated that to avoid the most detrimental effects of climate change, the world's electrical energy systems must stop producing carbon by 2050. With that deadline in mind, Dennis and his research team are racing to start making fusion available as a clean energy source starting in the 2030s. That way, they'll have time to integrate fusion energy into our existing electrical grids.
But our biggest hurdle is, or our biggest enemy is time, because we're running out of time.
If we're able to develop fusion as a clean power source, Dennis says it'll fundamentally change humanity's relationship with energy.
Fusion is just a completely unique arrow in the quiver and the battle against climate change.
Imagine that. Humanity's curiosity of those sparkling little dots in the sky led to scientific discoveries about stars, which may soon save our planet. Nova Now Universe Revealed is a production of GBH and PRX. It's produced by Terrence Bernardo, Jenny Cataldo, R.A. Daniel, Caitlin Falds, and Jocelyn Gonzalez. Julia Court and Chris Schmidt are the co-executive producers of Nova. Suki Bennett is senior digital editor. Christina Monin is associate researcher. Robin Kazmer is science editor. Robert Boyd is digital associate producer. Shyla Duff is digital video intern. And Devin Maverick Robbins is managing producer of podcasts at GBH. Special thanks to our guests, Hakeem Oluseyi, author of A Quantum Life, and Dennis White, director of MIT's Plasma Science and Fusion Center. I'm Alok Patel. We'll be back next week, which should be plenty of time for you to brush up on your out-of-this-world cooking skills before our next episode, where we'll share the recipe for creating a galaxy. It's like Interstellar Top Chef. If you're interested in learning more about the science behind the universe, visit pbs.org/Nova Now Podcast. This podcast has been made possible by the Gordon and Betty Moore Foundation.
GBH.